speaking about comparison between the sensitivities to the quasi-geostrophic and Ertel potential vorticity in the case of Typhoon Malakas.
Sorry, it's in Hurricane Ian. So I'm here to present some result I have for developing sensitivity to QGPV and to Ertel PV. And I'm going to apply them in the case of Hurricane Ian. And I want to acknowledge the support from my previous advisor, Dr. Michael Morgan, who for some reason I cannot list here for affiliation conflicts. Next slide. So we define the sensitivity as the derivative of the response function R to the state vector X. And the response function R can be any forecast aspects, so like sea level pressure or the total precipitation. And the state vector X can be your model output like winds, pressure, temperature, and water vapor. And the change in response function R can be expressed as the product of sensitivity and perturbation. We also use the Adjoint model, which is where you just transpose the forward linear model and it uses the final time Adjoint sensitivity as the input and integrates it backward, as you can see at the final line here, and it gives you the sensitivity at each previous time step. So for anyone who has taken GFD, you know the potential vorticity. It is a combination of relative vorticity and static stability, and is known for its two convenient properties. One is the conservation, which states for any inviscid and adiabatic flow, the Ertel PV is conserved along the isentropes, and the quasi-geostrophic PV is conserved along the isobaric surfaces. And the second property is the invertibility, which states for a given PV perturbation, you can invert winds and temperature around it. And we derived the sensitivity, the Adjoint sensitivity to PV following the Arbogast 1998, where you need expression for PV in two variables. You can use winds and temperature, and now I'm using the string function and geopotential perturbation to do that. And you also need an expression for your constraint, a balance constraint. You can find the operators T's and R's for size and fees, and do the adjoint of it, and you can derive the sensitivity to PV, so Q hat, and to imbalance A hat, as stated in the slides. So for the QGPV or sensitivity to QGPV, we use the geostrophic balance, and the QG imbalance A here is defined as a deviation of the geostrophic stream function 1 over phi hat, 1 over phi prime, from the total stream function psi prime. And we can solve for the sensitivity QGPV, Q hat, and imbalance A hat through the successive over-relaxation technique, which one used for inverting the QGPV. And for the Ertel sensitivity Ertel PV, we use the nonlinear balance equation as the balance constraint. It's much complicated than deriving the sensitivity to the QGPV, but in short, you first have to linearize the expression for Q and A, and you find the operators, and finally you solve for the Q hat using this equation. But the inverse matrix is really hard to find, so we kind of doing this by approaching the minimization of the similar expression in Q norm. And the main motivation and benefit of deriving the sensitivity to QGPV is that it combines the sensitivity to winds and to temperature together, and we want to introduce the PV sinking into the adjoint framework. So as you can see here in the orange, we have the positive sensitivity QGPV in the middle, and accompanied with that would be the cyclonic sensitivity to winds around it, and warm sensitivity above, and cold sensitivity below it. And you can invert geostropic balanced winds and temperature from the sensitivity QGPV, just like you can invert winds and temperature around the PV perturbation. And for the imbalance, if you have a positive sensitivity imbalance above and a negative one below, then it will require a cold temperature sensitivity in between to keep everything in order. I encourage you to check the sensitivity where I applied the sensitivity QGPV and to imbalance to a mid-latitude cyclone in my Monday poster, which I've uploaded to my GitHub. And speaking of Hurricane Ian, it has caused much precipitation and flash flooding, damaging winds and storm surge in Cuba, Jamaica, and Florida during its lifetime. And here I am investigating its first rapid rapid intensification period from September 25th 18Z to 26th 18Z, where it deepened from 1,003 hectopascal to 976. We used the WRF simulation to do the forward run in 24 kilometer resolution and 41 vertical levels in our time of interest. And the adjoint is carried out by the adjoint WRF, which is called WRF Plus. In the forward run, the storm deepened from 1,001 hectopascal to 978, which is quite similar to what we have in the real world. And we define the response function here as the dry column air mass in this red area. And that is to say that we want to deepen the storm at the final time and how we want to perturb or where's the most sensitive area for the storm to deepen in a later hour. And because the adjoint goes backwards, I'm showing all these plots in the backward sense. And on the left, you can see the sensitivity to winds and to temperature. Winds is in arrow and temperature is in shaded from the WRF Plus output. And in the middle is sensitive QGPV shaded. And on the right is geotrophically balanced winds and temperature inverted from sensitive QGPV. So at 850 level, we can see in general, we wanted more cyclonic winds around the storm center for the storm to deepen in the later hour and warm temperature sensitivity on the left. Of course, for a hurricane to deepen, you want it to be warmer at lower atmosphere. And in terms of QGPV, we want to put more QGPV near the storm center for a deepen in 24 hours. But strangely, when you're inverting the balanced temperature from it, you see a cold sensitivity at the lower bottom, although the wind is still cyclonic around, the wind sensitivity is cyclonic around the storm center. We see at 500 hectopascal, it still wants more QGPV for storm to deepen. And the sensitivity to, the balance sensitivity to temperature is actually showing some warm sign, which is good. At 200 hectopascal, you see a large pattern of wanting a negative sensitivity QGPV aloft, which may state we want more inertial instability at this level for the outflow to push outward and inspire secondary circulation for the storm to deepen. And again, you can see on the right, the balance component of the wind matches quite well with what we have from the WRF output on the left, but the temperature pattern, sensitivity pattern doesn't really match. Now we look at the sensitivity imbalance in the middle at 850 hectopascal, and on the left is again from WRF output, and on the right is the unbalanced component of the wind sensitivity and temperature sensitivity inverted from the A hat in between. Again, we can, not again, we see there's a good match between the sensitivity to temperature on the left panel and on the right panel. And they're both showing at lower level, we want more warm temperature for the storm to deepen. And the wind sensitivity is really small in this case compared to what you have in the balanced case. And at 200 level, we again see this match in temperature sensitivity in the left panel and in the right panel, and I should know the wind here. The wind sensitivity on the right is 5 times smaller than your total sensitivity to wind from the WRF output. And we want to take the cross section along the storm center, and then look at the vertical structure of sensitivity to potential vorticity. So on the left is the QG balanced one. On the right, in the center is the unbalanced component, and on the right, I combine them together and compare it with the WRF output. So if you have a positive sensitivity QGPV, as I stated before, you want a warm anomaly above and cold sensitivity below. That's why we have these cold sensitivity at the bottom for the geostrophic balanced one. And for the unbalanced components, try to correct that by throwing a lot of warm sensitivity for the storm to deepen. And when adding them together, the total feature matches the WRF output pretty well at lower troposphere, but not so much at the boundary layer across the storm center. Finally, we want to invest the sensitivity to Ertel PV, shaded in the middle, and you can see it's pretty much a mess. You don't have a clear indication of where do you want to put a definite positive or definite negative sensitivity QGPV And I'm plotting the sensitivity QGPV, sorry, the sensitivity to QGPV in contour. And on the left is sensitivity to imbalance. On the right is sensitivity. On the right is the Ertel PV background. So you see the sensitivity to Ertel PV stresses more on the to the northeast of the storm center and over the Cuba and the Dominican Republic. And I want to note that you can increase PV not just by adding more vorticity, you can also increase that by adding more latent heating or decrease that, which kind of correspond to what you see in Cuba. You may have stratiform precipitation to increase your latent heating release to increase Ertel PV at this time step. And Doyle et al. 2019 tried to investigate sensitivity to Ertel PV by adding a optimal perturbation, adjoint informed optimal perturbation, and compare the Ertel PV output from the perturbed run and to the control run. And we see at lower level, there isn't a much agreement. On the left is our sensitivity to Ertel PV, and on the right is the Ertel PV perturbation at lower level. But at 500, you can see some agreement of that at in the Central America, which is quite surprising for the storm to develop if it is quite far from the storm center and you don't really associate with that with the deepening of Hurricane Ian. And similarly, there isn't much match on the 200 hectopascal. So finally, to conclude, we've developed sensitivity to QGPV and to Ertel PV, and they have shown the ability to combine sensitivity to winds and to potential temperature together. And QG balance wind sensitivity explain majority of the wind wind sensitivity, while the temperature sensitivity is mainly explained by the unbalanced component of it. The sensitivity Ertel PV still needs much improvement. But there's some promising result that shows there's a spatial distribution similarity between sensitivity to imbalance and to Ertel PV. There's some similarity between the Ertel PV perturbation and Ertel PV sensitivity. Really thank you very much for listening, and I'm welcome to any questions and suggestions.
Thank you, that was great. No questions online. Do we have any questions here in the room? Yes, can you come to the mic? Thanks.
It looks like a lot of detailed mathematics went into this study. I'm curious, from a big picture point of view, what does the method tell you about your model that you couldn't learn without doing this?
I'm sorry, what can I learn without what?
I'm just saying the context of the work, what the technique you're working on, what does it tell you about the model that's new, that you couldn't learn without doing the inversion and the sensitivity?
So previous study only stress on one sensitivity, so like wind sensitivity, or they say we want more temperature, and the PV sinking actually combines them together and provide a more unified view of seeing that. And it is more important to understand the things dynamically instead of looking at each variables separately. So that I think adds a lot of knowledge or scientific knowledge to the case study.
Okay, thanks.
Thank you.
Yeah, we can do one more.
I have a question. As you may know, the Ertel PV and QGPV are dry PVs. Have you tried use most PVs, like replacing the theta with theta E or MSE in the?
So it's really
PV?
hard to do adjoint in terms of moisture because it's highly nonlinear, and the adjoint model is linear. But we're trying to in the WRF code, you can actually relate the water vapor with the vertical motion and temperature perturbation. And I think it's possible to include moisture in my PV, sensitivity to PV. Thank you very much.
Sorry, was that you, Kevin, back there? Yeah, we could go ahead.
So I noticed that you ran your model at 24 kilometers. Do you have any thoughts on the role that convection may play? Because you're going to be parameterized convection in that model. And so I'm curious if your thoughts, so also the PV inversion techniques, they can't handle negative PV, right? So you have to make an assumption that it's either any sort of negative PV would be 0 or very small. So I'm curious what your thoughts are on the existence of negative PV and the role that that may play if that's contributing to any sort of, like, you say that it explains majority of the temperature. I'm wondering if, you know, any would be explained by the potential existence of small scale negative PV.
Yeah, so to answer the first question, when you're running a WRF model in a really small resolution, it is pretty hard and you can get messy features in the sensitivity analysis, and that's been tested by a lot of people, and they try to get away. And the sensitivity study or the adjoint cannot be done in nested framework. So that's one of the reasons that we're not using the final resolution. And to answer the second question, the minimization technique actually doesn't require a positive PV. So, and in the Arbogast, they kind of use this to invert the, I think it's the symmetric instability, and they kind of know the same thing for the minimization technique to be used in inverting the winds and temperature.
Thanks, Noah.
Thank you so much.